Oh, look at that. Well, I'll begin with a word of prayer. Dearly Father, we thank you for this day. I thank you for these students, this class. Just pray that you'd be glorified at what we do. Help us to just do our best, Lord, for your glory. In your name I pray, Lord Jesus. Amen. All right, so let me just talk about some mundane things in here. I gave you guys the course planner, which of course basically is, the syllabus. I'm James Cook. I guess you know that. But this is my website. Let's see here. www.supermath. I don't guess I put a link to this in that announcement I made, but if you just go back to the, I think I maybe gave you a link to this one. This is the course website, which is just a sub-page of my page. Anyway, so getting back to here, this right here is my schedule. At least for now, I'm kind of waiting for Dr. Sprano to schedule his Galois theory course, which is an unusual event here. But yeah, I have office hours 9:10 to 10:30 Monday, Wednesday, Friday, and then also again from noon to 2 Monday, Wednesday, Friday. Those are the office hours in here. I'm in the math department. And but this might change because I'm waiting to get Dr. Sprano to schedule the Galois theory course, and then I have a research meeting I'm hoping to have with a student once a week. And so, but that student's in the Galois theory course, so I'm kind of up in the air about that. But yeah, and these are the other courses I'm teaching. Maybe some of you are in some of these courses. I can't remember. Anybody else in other class with me? Pedro, yeah, and. Linear algebra, okay. Yeah, I will eventually not remember, but it's not that I don't want to remember, it's just I have to accept my failings. I can never make it in business. I don't remember names enough. But if you take enough classes with me, eventually I'll know you. Let's see here. So, yeah, those are my office hours. Any questions about that? No. So, let's see here. This is the course website, and there's not too much here, but I have a link to an electronic copy of the course planner that I made you a printout of. Number 2 is important. These are the lecture notes. I've also, I also put a copy of these in Canvas for you guys. But if you look here, it's 150 pages. Basically today, I'm hoping to cover more or less sections 1.1 and 1.2 in here, something like that. All right. I'll try to write down a fair amount of what's in the notes on the board, but I won't get everything written down. So it's important that you read the notes to fill in whatever I don't get written on the board, just to complete the knowledge. All right. So there's that. So I'm not really using the book for a couple of different reasons. 1, I don't like it. 2, I don't have a copy of it. 3, I bought a copy of it, but I don't know where it is. My daughter took this course a year ago, and I bought her that $100 book. And then she gave it to her brother, who's been asked to find the book for several months. Anyway, I still don't like the book. I do have a PDF of it, so it's It's not, the book has many good practice problems, so it's not, if you have a copy of it, it's not the worst thing. But we are going to follow my notes. There are required homeworks I call missions in honor of Naruto. So mission 1 is on basic logic. Here's a copy of it, a PDF. You'll need to print this out for yourself. And so you get paper, you work these problems out on paper, and you turn your solutions. You're allowed to work together. You must, of course, explain your steps. We don't just create answers in here. The whole process is the answer. Failure to write things in proper sentences and stuff will cost you points, things like that. But anyway, I do have a grader, and so hopefully you'll have a lot of feedback from the homework this semester, and my expectation for the grader is that it gets graded fairly quickly and gets back to you. So hopefully that'll actually happen. Yeah, so there's a homework due just about every week. Let's look at when things are due. I say due, but I really should say collected. There's a homework collected every week, the due date is always a day before the class that it's collected. In this way, everyone has extra time all the time. So if you ask me for extra time, the answer is yes, you already have it. Very good. The reason for this is I really can't field late homeworks because I post solutions to the homework once I collect it. So I can't very well take late homeworks when I'm posting solutions. And I don't really want to derail the whole structure of the class just because some people can't turn homework in on time. So this is, kind of a problem for me in that I post homework solutions. I can't really take late homeworks reasonably and be fair to the other students at the same time. But anyway, I don't think the homework is too much. You do need to make time for the homework, and I hope you learn a lot from it. That's, I spend a lot of time putting together these homeworks. Now, if you're reading a homework problem and it doesn't make sense to you, email me. I do respond to email. I'm interested in knowing when my homework doesn't make sense. I'm very interested in that. I prefer to find out like before the day before. But how many people here are engineers? Okay, so everyone else doesn't procrastinate. No, I'm just kidding. I mean, everyone procrastinates. But for engineers, procrastination is a virtue, So to complete a homework is great. To complete a homework the day before it's due is amazing, right? Something like that. But I love engineers, don't get me wrong. Let's see here. Part of the reason I came to work here is I have always had hope that we would have more sort of interplay between the math and the engineering department long term. Okay, so what else can I tell you? There is a quiz a lot of days, like Thursday there's a quiz 1. Nothing to be scared of, you just need to pay attention to the definitions today and you can expect one of those definitions to be quizzed Thursday. So it's probably going to be something like write the truth table for conjunction and disjunction, write the truth table for implication, something like that. Whatever we define clearly today, right? Those are possible quiz questions for the next class, and that's kind of how it's going to go. So as we define different things in here, it's important, like of utmost importance, that you memorize those definitions and come to an understanding of them as soon as they're said, because after we make a definition in here, we keep using it. So every day that you don't know the definition and haven't memorized it is a day that you don't understand the next class. So to get the most out of the course, it's important that you study as you go, and that way we'll all be smarter when we leave the class, me included. But anyway, there's a bunch of quizzes. I actually have 12 of them. There's 100 points in your syllabus, so like 20 points extra, which means essentially you can drop 2 quizzes. Or you can keep the 20 points extra to make up for 20 points you miss on a test somewhere. All right? Any questions? No? Okay. So, this is a pretty standard course as these go. We start by studying, logic and proofs. Then I transition to talk a little bit about what's called set theory. Really, we'll study naive set theory. Then we have a test. Then we'll turn to studying induction, equivalence relations, and partitions. Then some sort of deeper things about integers, the well-ordering principle, the division algorithm, Euclidean algorithm, and so forth. We'll look at this example called modular arithmetic, which is one of the most important things we'll learn in this class in terms of when you guys go take the Math 421 class rather. That's one of the central examples in there. So we've got a couple different goals in here. One is just to learn how to write proofs in mathematics. That's our main goal. But our other goals are to become more familiar with the basic examples that we use in higher level math. We'll spend then a few weeks talking about functions. You think you know about functions, that you don't. There's more to learn. And then we finish the class by talking about cardinality, which is the study of the size of sets, basically. And then finally, there's a little bit of calculus proofs. You remember those epsilon delta proofs? Yeah, they come back here. All right, so we'll get back into those. Hopefully that stuff will make a little bit more sense after you have a semester of quibbling over words, as opposed to epsilon deltas kind of hit you upside the head in Calc 1. You don't really know what's coming. Although there's a couple things like that in the calculus sequence, right? The whole discussion of series and sequences in calculus 2 is 10 times more sophisticated than anything else we do in the calculus sequence. It really doesn't belong in that course, pedagogically speaking. But it's a matter of custom, so we have to do it, But if you really think about your experience in calculus, you'll realize that that discussion of series and sequences in the middle of calculus 2 was at an entirely different level of sophistication than everything else we do, pretty much. It's kind of a weird thing. But it's there for historical reasons. And then finally, we'll end the course with kind of an overview of some algebra and maybe just a kind of big picture of what the math major is, that kind of thing. So I am here to help. So you guys have questions, you just ask, right? You can always raise your hand or just, politely interrupt me. And if something doesn't make sense in here, we'll try to cover it as much as we can. Let's see here. The grading is relatively simple. There's 200 points for test 1, 200 points for test 2. The missions are worth 200 points altogether. Each one's worth 20 points. Quizzes, there's 100 points there, and then finally the final's 300 points. So, and it's the usual, A, B, C, D. I'm obligated by university policy to use 1,000 points. I have no freedom in the matter. Although the year before they started making this a requirement, I had a 10,000 point syllabus. See, up to that point, the 1,000 points was just a suggestion. It wasn't a requirement. So I decided to take their suggestion and multiply it times 10. I argued that my point system was 10 times better than theirs. Unfortunately, I'm no longer allowed to use this, but I'm told by the students it was very scary because they had like 1,000 point tests. It was like, you come into a test it's worth 1,500 points. It's very unnerving. But on the other hand, it was nice because all the homeworks, you could make every homework problem worth like 10, 20 points, something like that. So then you can give 7 points of homework. Nobody wants to work with 0.7 points of a homework, like graders. So anyway, I will shut up about all that. Let's get into the math, if I haven't forgotten anything. Have any questions? No. Let's see. I'm going to hand this around. I think most of you already checked it, but I don't want to call the names of people who came in late, so I'm just going to hand it around. And I don't really think you guys were that late. I'm just, Some other people who aren't here are late. That's another matter. You know who you are. All right, so I probably will use the projector some today because there's some theorems later which have got quite a bit in them. But, all right, will you go up now? Go away. Go away. Shoo. All right. Aha, figured it out. So, this is not a course in logic. So what I have to say about logic is necessarily a little bit informal, but maybe it's more formal than what you've seen before. So, like this, the formal study of logic is very old, right? I think the ancient Greeks were really, I don't know, you could say the ancient Greeks initiated the study, but I think pretty much as long as there's been humans talking to each other, there's been logic, right? And you could argue, of course, that, God knows logic, and so as long as God has been around, there's probably been logic. So it's very old. But anyway, we'll begin with a definition. And here it is. A proposition is any declarative sentence, including mathematical sentences such as equations that is true or false. All right. If P is a propositional variable, then P equals to T, or P is equal to f. I'm changing the definition a little bit here just for the sake of our, so this means t equals to true, f equals to false, all right? So a propositional variable, it's either true or it's false. And a proposition is itself any declarative sentence, including mathematical sentences, that is true or false. A predicate or open statement is a proposition whose truth is a function of one or more variables. All right. So this first week we're talking basically about either propositional logic or predicate logic. Propositional logic is about statements which are true or false and don't really involve other variables, whereas a predicate or an open statement is a proposition which only becomes true or false if you know the actual values of these other variables. So an example is probably helpful. Let me find a marker here. Like, so x greater than 5. What do you guys think? Is this a proposition or is this a predicate? Yeah.
Proposition or predicate?
Predicate, yeah. That's good. That's good. Why is that?
Because it depends on what x is.
Exactly. Because we don't know if that inequality is true or false unless we know what x is, right? Okay, so how about this? X equals to 10 and x is greater than 5. Right, x equals to 3 and x is greater than 5. How about these sentences? Let's go with let me give these labels 1, 2, 3, just for the sake of discussion. So we already said that 1 is a predicate. How about 2? It's a true proposition. Very good. And how about 3? Again, it's a proposition, right? Is it true? No, that's not true. So if you're looking for me to prove to you that that's true or false in here, that's not going to happen. So we do have to assume we have some basic intuitive understandings of basic arithmetic in here. We'll always be working with those sorts of things. So, all right. Goodness gracious, I got to tell Dr. Joseph just to not erase the board. I'm going to go through like 2 gallons of this stuff this semester otherwise. Yowzers. Well, eventually. I guess that's good enough. All right, so next definition is our first example of a logical operation. Although I guess, I'm sorry, I let me stop here just one more second here. Example 2. Erasing the board, it erased my mind too, apparently. So how about this as an example? The dog is beautiful. What do you think? Is this a proposition?
Yes.
Yes. Dog lover. Other opinions? Yeah.
No, because beautiful is subjective.
Beautiful subjective. Yeah. See, so this is the kind of example I'm going to try to avoid in here because this is not productive, right? It's very much a matter of you could disagree about whether or not this is a true statement or about whether or not I mean, maybe other people would say, well, this is really a predicate, right? Because the truth depends on who's saying it, right? Like the variable of this predicate is hidden. It's basically the speaker of the sentence, you know? So you can kind of have endless, I think, mostly uninteresting discussions about whether or not that's a proposition or predicate. I think usually something like this, I'm trying to think of another good example. Well, how about you guys? You guys have another example of a sentence which would not be, which would neither really fall into the category of predicate or proposition? Are there such things? I'm going to go on here. So definition. So what I'm trying to tell you is I'm going to attempt to avoid this kind of thing in here because I'd like for our focus to be on things where we can decide whether or not we're talking about something that's meaningful with mostly a focus on math without, although some of the examples we're about to get to, you'll see that I don't really stick to this entirely. Anyway, let me go on here. So let P, be a proposition. So what does that mean? We define the negation of P by what's called the truth table. So the truth table is just a way of communicating case-wise logic. So we'll put like the variable here and the thing we're defining over here. So if P is a proposition, it's either what? It's either true or false. Yeah? Now this symbol, squiggle P, all right, that's read not P. So this is read not P. So this is the negation. You can go over there, there's spots. So the negation of P is read not P. And so here's the way this works. If P is true, not P is false. If P is false, not P is true, all right? So this is the negation. So this is a logical operation. A logical operation is something that we take in a given propositional variable and we output something new. This particular one just involves one propositional variable, right? There are, so this is the negation. We'll use this a fair amount. There are three others, what are called unary, I can't speak today. Oh, good grief. Did I not write it down? Oh, there it is. Every so often you forget how to spell something and it's just, there's no way to get it back. So if we think about just one logical input, right, there are 1, 2, I'm just calling them 1, 2, and 3. There's basically, these are the only logical operations you can think about with one propositional variable, T, F, right? So number one, you can just make the output just be what the input is. So number one is what I would call the identity. You know, it's the identity function. Now we'll talk about functions more in depth later in the course, but we'll be using the term function as we go here with the understanding you guys talked about functions for a while now, right? So you know what a function is. You give it an input, it gives you an output, right? And there's just a single output, that's a function. So the identity function just takes in, it takes an input and the output is the same. That's the identity function on the set of true and false. That's one thing you could do. The other thing you could do is you could just have it always be true, or you could have it always be false, right? So like 2 is, constant truth function, and 3 is the, and these I don't expect you to memorize. I'm just talking about this, okay? Constant f function. But if you think about just one input, this is it, right? Because if we're talking about true and false, how many different ways are there to assign one propositional variable? Well, there's just these 4, right? There's negation, the identity, the constantly true function, and the constantly false function. So what happens if we move on and we start talking about logical operations on 2 propositional variables? So, oh, well, thank you. So begins the story of how I headbutted a student. Not careful. So definition here. Let P and Q be propositions. I'm going to abbreviate that as prop, if that's okay with you guys. We define conjunction, which outside of this course, I never use that term. Or logical and. That's more what I would say anywhere else but here. All right, bye. And no one really has any trouble with this one. This symbol might be new, P wedge Q. So that's the symbol for logical and. So that's read as P and Q. And P and Q. And so here we can have P is true, Q is true. We can have, wait a minute, let me make sure I use the same format as the notes. Oh, I started with false, false. Let's start with false, false. So for you guys who are engineers, why am I doing false, 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 true, true, false, true, true? Why would I do that?
False is a 0 and true is a 1.
False is a 0 and true is a 1. And so what am I doing if I'm doing this? What's the order here then? Like why? Yeah.
Counting from 0 to 3.
Yeah, it's counting from 0 to 3 in binary, right? Now, that is not part of this course. We have just entered the realm of Math 250, right? When I took this course as an undergraduate, I had just got done with a 2-year degree in electronics and a semester of electrical engineering. So when I took this course, I asked the professor if I could write 0 and 1 instead of T and F, because it just was easier for me. And I was like, and he said, yeah, sure. So I guess I would give you guys the same freedom. If you would rather use 0 for false and 1 for true, I guess I'll allow that for this part of the course. However, I do insist that somewhere on the paper, preferably at the start before you do it, you write, I'm using 0 equals to false and 1 equals to true for the purpose of this truth table. That sentence must be written so that the grader won't feel bad about not taking points off. She's kind of a monster. Okay, that's not true, but I'm not talking about my wife, just to be clear. She's too busy to grade. So false and false is false. False and true is false. True and false is false. True and true is true. The only way to have logical and be true is for both the P and the Q to be true. Now P and Q here, P and Q are called conjuncts in this context. All right. The conjuncts are the things that are forming the conjunction. The next logical operation that we need to talk about definition. Let P and Q be propositions. Define disjunction by, here's this truth table. So you got your P, you got your Q, P. So I guess, well, it's just, this is read P or Q in here, all right? So P or Q. So it's like a V, but, well, this is like a V. The other one's an upside down V, right? Yeah. So again, since we have two propositional inputs, we have 4 cases to deal with. And I'll try to make and I expect you to do the same for the sake of all of our common sanity. Let us agree that it is our custom that the truth tables be written in proper order. You know, because you could see how if you were a grader and everybody just decided to do a different order for their truth table, it could get really annoying really fast. So let it just be agreed upon us, our pact, our custom here, that I will take points off if you do anything other than this ordering for the sake of our common sanity. But this is disjunction, and so this is P or Q. And the way disjunction works is if either one of the inputs or both is true, it's true. P or Q is true. So the only way this can be false is actually the first case. The other 3 cases, it's all true. The disjunction is true, P or Q. Now, this is obviously not how we use the word or in common English language, is it? Right? Like I say, you know, I own a pet, you know, I own a single pet, which is an aardvark or a cat. This would not be a logical sentence, right? Because if it's a single pet, it can't be both an aardvark and a cat, right? But mathematically speaking, mathematical or, right? That would be like a true sentence. So this is probably the most dangerous thing in terms of mathematicians perhaps being misunderstood. Our use of or is, you know, a little bit different than the typical use of or in sentences, English sentences. The other kind of or, let's see here. This is also known inclusive or. Mathematical or, you could also call it inclusive or. All right. On the other hand, what we commonly use in sentences in English is what I would call exclusive or. Exclusive or it's a false statement if they're both true, right? Like the aardvark cat example I just gave. All right, so exclusive or. Here's another one. So P, Q propositions. The truth table for exclusive or, and we do have a symbol for that, which is this, P plus circle Q. We don't use this one too much, but here it is. So we've got false, 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 true, true, false, true, true. So exclusive or is the one that's common in conversational English. It's only going to be true if there's just one. So this is true, but false, 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 and true, true are both also false. This is the so-called P exclusive or Q. All right. How many logical operations are there on 2 propositional variables? Did you guys count? How many of these do we have to go through? I've gotten through 3 so far. How many more do we have? And do we have enough time to go through them all? How many are there? What's that? I couldn't hear. There were 4 unary. How many? These are binary, right? Binary operation has 2 inputs. So logical conjunction, disjunction, exclusive or, these are all quote-unquote binary operations, yes.
Would there be 16?
There would be 16. So we're not going to go through them all. And they don't all really have names, as far as I know. But there is one other one that has name that's very important, which is, again, P and Q propositions. Define, so here we go. We have P, we've got Q, and this is implication. Now, I think the book uses a single arrow. It might. I insist on using double arrow for implication in here. So here we go. False, 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 true, true, false, true, true. I may also insist that you use 0 and 1 if your handwriting is so horrible I can't tell the difference between false and true. But as a general point of order, if I can't understand what you write, I assume it's wrong. Just so you know. Burden of proof is on you. That's this class. But anyway, so this is the P implies Q. This is read P implies Q. There's a bunch of different ways to read this, and I'll probably get the projector out here in a second because I don't want to write them all out. But here, P is called the the hypothesis or antecedent. And Q is called the conclusion or consequent. All right, those are other names for these. And you can, there's space. You can walk in front. It's fine if you want. You might appear on the YouTube, but it's okay. Now, so this is implication. Now the question is, what are the when is the implication true? False implies false. By definition, this is true. False implies true. Also true. True implies true. Also true. The only way an implication can be false is if you have the hypothesis is true, but the consequent is false. That makes the implication a false statement. So this is how implication works. All right. So this makes for all kinds of silly and fun examples. Like here's my example, if I can find it. Come on. Oh man, where's my example? Oh, there it is. Well, let me get the projector out because you don't need me to write this stuff out. We just want to look at it together. Let's see here. All right, so here's where we were. Almost. Well, oh, it's thinking. Actually, let me use the projector to get through the rest of the definitions for today so that we still have time to do a proper truth table proof with the time that remains. That's probably more interesting than me just writing out definitions you can read, right? So, but we do need to have them on our mind together. Yeah, it was too bright. This is better. All right, so this is the implication or conditional. As I was just telling you, it's only false if the input is true, but the output is false. This is the one thing that makes an implication false. Some other language we need to be aware of. The Implication Q implies P is called the converse of P implies Q. These are not logically the same. What does it mean for two binary operations to be like logically equivalent? Or just generally, what does it mean for two statements to be equivalent logically? It means that they share the same truth values for the same inputs, right? This, on the other hand, is the inverse. Not P implies not Q is the inverse of P implies Q, right? And then there's also, come on, the contrapositive. The contrapositive is not Q implies not P. That's the contrapositive of P implies Q. That one's important. You need to remember this, all right? So, just here's a silly example of all three of these ideas. So here's the implication: if a cat is alive, then it is evil. This is a true sentence. So this is exactly the kind of thing I promised I wouldn't do in here, but I'm just going to do it for the sake of comedy, if you'll allow me. So, although comedy may be too strong a term. So here, P is the proposition that the cat is alive. Q is the proposition that the cat is evil. All right. Which, again, this right here, alive I think is clear enough, right? Alive or dead, that's a propositional statement, I think we can agree. Either a cat's alive or it's dead, right? Ignoring some sort of extended and uninteresting conversation about whether or not zombie cats exist, Given current medical technology, certain, life-altering drugs, blah, blah, these conversations can be had, but who cares? Q is the proposition that the cat's evil. So the converse, Q implies P, would be the sentence, something like this: if the cat is evil, then it is alive. All right. This is also a false sentence because it is possible that the cat is evil, which is the true, a true hypothesis, and yet it could be dead, right? You could have a dead evil cat. So this implication actually here is false. But anyway, let me shut up. The inverse, not Q implies not P, would be if the cat is dead, then the cat is good. Here I'm suggesting that the negation of alive is dead, and that the negation of evil is good. I think that's reasonable. The contrapositive, not Q implies not P here, is if the cat is good, then the cat is dead. That makes sense. So, sorry, my mom watches these. She's not going to like this one.
Q and P is supposed to be swapped from the inverse.
The converse?
Or the inverse.
Maybe.
It's the same form as the contrapositive.
Yeah, that's a typo. It's supposed to be not P implies not Q. Did I actually? See, I wrote. Very good. Thank you. Excellent. So I need to fix that. There's a typo here. But this typo is not reflected in the sentence, though. So the sentence is good, but this needs to be fixed. Thank you. Excellent. As I should tell all my classes, if you see something, say something. It's less true here because I'm not teaching at 8:15, but it's even more true at the 8:15. Okay. So it's annoying, but implication, I would love that every time there was implication in a mathematical sentence, it arose in the format, if blah, then such and so forth, right? Because that is almost always a clear implication. It's a way of writing an implication in an English sentence. But there are a bunch of ways that implications can be written. And so I'm actually following this book by Wolf. These examples are more or less from Wolf. So here's, P implies Q is sort of the general format. So differentiability of F implies continuity of F. That would be this kind of style of sentence. If P, then Q. If F is differentiable, then F is continuous. If F is differentiable, F is continuous. The function is continuous if it's differentiable. The function is differentiable only if it's continuous. Differentiability of F is sufficient to give continuity for F. Continuity of F is necessary for differentiability of f. Whenever f is differentiable, f is continuous. And finally, the function is continuous whenever it's differentiable. These are all logically equivalent sentences, but as you can see, the grammatical structure of them is quite different. Some of these sentences I find unnatural. I usually, as a point of mathematical writing, use the if-then construction because I feel like I lose less of my audience with that. All right, but you should be aware that that's not the only way you can write an implication in a sentence. And generally speaking, what this all means is that you really need to think about converting a given English sentence to like a corresponding propositional sentence. So I should say a symbolic sentence, right? So if every one of these up here, like symbolically, that whole list was P implies Q. Every one of those could be understood symbolically to be P implies Q, but grammatically they're all different, you know. So there's also the biconditional equivalence, which is P. This is read P if and only if Q. So this is actually we already wrote this, didn't we? Oops. I think my notes, you know, guys, I work hard to get these notes ready for you guys, but it's just a fact of life. I only have a Christmas break to write these notes. And try as I may, you know, I don't have an editor, so you guys are the editors. What do you think? Oh, no, these are not the same, is it? Ah, okay. So let us, I'll leave that up there for a second. Let me show you a very easy truth table proof, given what we already have in front of us. And then I'll do a proof, and then I'll do the next proof I'll do in its entirety. Okay, so if we go back to this definition, and if you want to, maybe write it again, I don't know. If we negate P exclusive or Q, what's that do? How do you negate something? It's just true becomes false, false becomes true, right? So very simple. False becomes true, true becomes false, true becomes false, false becomes true. But what is this? This is the same as P if and only if Q, right? So this is read P if and only if Q. So that itself is a shorthand for if and only if. Do you agree? See, this is the definition of the biconditional, right? The biconditional P if and only if Q is how that's read. We have true, false, false, true. The negation of the exclusive or is also true, false, false, true. Therefore, what does this all prove? Thus what? Oops. That was dumb. We're going to need that. Thus, not P or Q is... so this is... oh, man. This is kind of funny. So this right here is an example of a tautology. So this is an example of a tautology. What's a tautology? I think I need to plug in my computer is what's happening here. Oh, so a tautology is a statement that's always true. All right. So like for the unary operations we looked at, a tautology would be like number, what was it? I've covered it up, but number 2 was a tautology, which is kind of silly. It's just always true, right? A tautology is always true. Come on. So it is always true. Like whenever this is true, this is true. Whenever this is false, this is false. All right? This is a tautology. These are logically equivalent binary operations. All right. One of our, so let's do a couple of other of these. So I think towards the end of mission 1, I've asked you guys for a proof that, a proof of certain tautologies, all right? And they're all kind of stated this way. Now, the other way that these, sometimes we use the if and only if arrow for a tautology. The other language which is sometimes used is something like this. So P implies Q, right? Let me just use this again. This is true. It's logically equivalent to this one. Oops, not Q implies not P. So this is a logical equivalence. Now, how would we? This is a claim. So let me just call this a theorem. A theorem is. So here's the proof by truth table. So we have true, we have false. My bad. We have P, we have Q. All right. Then I will put P implies Q over here. And then I will put not Q here. I will put not P here. And I will put not Q implies not P here last. All right. This is not in the notes. It may or may not be one of your homework problems. I don't remember. There's a danger that I'm doing your homework, but it's a danger. I accept that. That just means it's interesting. So, all right. We've got false, 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 true, true, false, true, true. There we go. Our standard ordering of cases, right? And now we can fill out the table. So by definition, what do we have here? We had, the only way this is false is if we have true implies false. So this is the false case. The other 3 cases are true for the implication, right? Negate Q, how do we do that? We just look at column 2 and we do the opposite. So we've got true, false, true, false, right? Not P. We look at the first column, we do the opposite. So we've got true, true, false, false. Yeah. Now, it's not written in stone that you have to do these columns in this order, right? I could have just as well, I could have written the not Q and the not P over here. There's a freedom. There's more than one freedom in how you would formulate this proof, right? The one that just sort of pops up at me immediately is like, well, why did you write the columns in this order? I don't know. It just came to mind. All right. I can't explain that to you. It's just what I chose. And you might not think it's maybe you feel strongly that I should have put the not Q and the not P first, and then I should have put this one last. That's probably right. You're probably correct. That probably been better. Okay. So then over here, what do we have? True. Is true implies true, true? That's true, yeah. Is false implies true? True?
Yeah.
That's true, yep. Is true implies false true? It is not. False implies false is true, all right? Thus, P implies Q is logically equivalent to its contrapositive, not Q, implies not P. So this is what's called a truth table proof, all right? So since I've got this thing out here, let me just show you in the homework which ones are kind of, I'm looking for a very similar kind of argument. So let's see here. So if we look at the homework for a second, you know, problems 1, 2, and 3, I think, are just really about understanding the logical operations. You know, problem 4 is, you know, a grammatical problem to try to convert a sentence to a propositional symbolic thing. Shout out to Goku. And then here is one of those, I give you the meaning of the propositions, you put together the English sentence using conjunction and disjunction and negation. That's kind of fun. And then problems 6 through 10 are all proofs, all right? These kind of proofs are proved with truth tables, or the other possibility is using a symbolic logic proof, all right? I'll try to give you so a symbolic logic proof basically makes use of other tautologies to establish a future tautology. So there you don't actually have to use, you know, well, we need a little bit more before we can do one of those. We don't have enough in front of us yet to do it properly yet. So have I done any of your homework? Phew. No. All right, good. So like, how would you do number 8, for example? What would you do? You want to make a truth table, right? You put P, you put Q, and you work towards making one of the columns being this statement, right? And you make another column that statement. Well, you make the other column anyway, you have to build that logical statement there. And then if it's a tautology, it will always be true. Right? To prove this is a tautology would be like proving that's always true. All right, so let me get back to the notes here again. Just a little bit on like notation. Order of operations is that we do negation first, and then and or, implication, and finally, last but not least of all, the biconditional. However, the unfortunate thing is there is no general agreement on which comes first, the and or the or. So we kind of need to have parentheses. If you've got something that involves and or, you really need parentheses because like this and that are not logically equivalent. So we need parentheses if we've got and or. But on the other hand, if you had something like this, the not comes first and the and comes second. The implies happens after that, and that comes last. So like here, this is logically equivalent to that. See, I put in parentheses so you can see the order of operations without, you know, doubt. I, as a general point of order, put in more parentheses than I need in the interest of not losing students. That's one of my vices. So I've been talking about this all along. Truth function. You know, I've been saying P and Q is true, meaning that, you know, the conjunction is true or the disjunction is true. So I don't know. I have a hard time separating this definition from what I've already said. But anyway.